Hello there, and welcome back. In this video, we're going to be focusing primarily on two special cases, or one could think very important properties associated to the probability of two or more events. So let us just briefly go over some of the main important concepts that we've discussed up to this point. So if we have E to be some event in some sample space S, then we define the probability of that particular event E as the quotient of the cardinalities of the event space and the sample space, respectively. With that definition, one should be able to prove that the probability of any event is always between 0 and 1. Also, if you have a bunch of different events that are mutually exclusive in that particular space, then the sum of all of those probabilities must come out to 1. If you have two or more events, then one could ask questions such as the probability of A or B, or the probability of A and B occurring simultaneously. If that is the case, the probability of A or B can be found by the probability of A plus the probability of B minus the probability of A and B occurring simultaneously, and the probability of A and B occurring simultaneously can be found as the probability of A times the probability of B, assuming that A has already occurred, which we refer to as the conditional probability. Now, of course, if A and B are independent events, the probability of E2 would just be E2, because it doesn't really care about E1. And the backwards version can also be said about E1 given E2. If E1 and E2 are mutually exclusive events, which I will just abbreviate as ME, then the probability of A and B occurring simultaneously is equal to 0. And if A and B are independent events, then the probability of A and B is just going to be the probability of A times the probability of B. Now, with these rules only, one could technically solve any type of probability problem if one is willing to list out all of the event spaces and sample spaces. So what I want to start off with is a very complex example that sort of uses a combination of all of these different rules, and then I'm going to sort of show you a little shortcut that one could use for problems of this structure. So the problem goes like this. Suppose you have a room of 10 different people. So one could think of this, for example, the 10-letter string of that, you permute and get a bunch of words. But we have a little bit of repetition in regards to one particular characteristic. So these people are all different, but 4 of them have a white shirt and the others having a blue shirt. Suppose you pick a simple random sample of 3 people from this room. What is the probability that exactly 2 of them in that set of 3 has a blue shirt? Okay, so let's just begin by listing out what we are sampling from. So I guess you could call this the population of people. So how many white shirts do we have? I have 4 white shirts. So I'm going to call those people W1, W2, W3, and W4. And then I have 10 people total in the set. That means the remaining have blue shirts. So I'm going to call this blue 5, blue 6, blue 7, blue 8, blue 9, and blue 10. Keep in mind that not necessarily do I need to write this as WWWWBBBBB because I'm interested in having different people in my sample, right? So that's why I've indexed these things from 1 to 10, indicating person 1 through person 10, in addition to the special characteristic that is associated to their particular shirt color. So what does it look like in terms of my possible samples that I can be drawing from, right? So this is going to be my sample space because what am I looking for? I'm looking for a particular set of 3 people that has some special criteria associated to it. So my sample space is going to be a set of 3-person teams, and my event space is going to be the set of 3-person teams that have exactly 2 people with blue shirts in them. So let's just list out just a couple elements of our sample space just to get an idea. So what we could do is we could select W1, W2, W3. We could select W1, W2, W4. We could select W1, W2, B5. And we could also select W1, W2, B6, and there's several more where W1 and W2 would be elements of that 3-person team. You could also have mixtures, for example, W1, B5, and B6. You could also have W3, B7, B10. You could also have, let's get rid of these white shirt sets. So one could also have, say, B8, B9, B10. Why not? And one could also have B5, B6, and B10. And there are, of course, several different elements that I could have in this set, but these are some of the 3-person samples that I could have. Okay? So we need to figure out what the size of this sample space is, right? So how are we going to do that? So let us first observe that W1, W2, W3, and W3, W2, W1 are the same exact set with respect to actually 2 different criteria. So these are the same with respect to 1, the people, and the characteristic, these are all samples with 3 white shirts, right? So these are all the same in regards to these particular categories, but I'm actually going to be focusing on the color shirts categories. So this is actually, in terms of when I say order does not matter, this is what I'm actually going to be primarily focusing on, right? Because you cannot select the same person 3 times because we're assuming without replacement since we're doing a simple random sample. So these are the same exact set. So that means we will be using combinations for this. So that means how many 3-people sets can I get from a set of 10? That is going to be 10 choose 3. So that is going to be equal to 10 factorial over 3 factorial times 7 minus 3, the quantity factorial. 10 minus 3. 10 minus 3. So that's going to be equal to 10 times 9 times 8 times 7 factorial all over 3 factorial times 7 factorial. The 7 factorials will cancel. 3 times 2 is going to be 6. So it's going to be 10 times 9 times 8 divided by 6. And then what can you do? So 6 is the same as 3 times 2. So it's going to be 10 times 9 times 8 all over 3 times 2. So that's going to be equal to 10 times 3 times 4. 4 times 3 is 12, and 12 times 10 is 120. So therefore, the size of my sample space is going to be equal to 13 choose 3, which is going to come out to 120. So how can you interpret this particular number? So this is the number of different 3-person, I guess you could call them teams or groups or samples. Either one would be fine. So that is my sample space. Now let us look at my event space that I'm interested in. So my event space needs to be a subspace of my sample space, and we need to only focus on our 2 blue shirt samples. So some of those samples would be W1, B5, B6. You could also have W2, B5, B6, and you could also have W4, B5, B6, and there are several others that you could list here as well. And keep in mind, we're assuming that this set and the set B5, B1, B6 are the same, and therefore we have not included them in our sample space, so therefore we should not be including them in our event space. So just keep that in mind. All right, now notice I'm focusing on white, blue, blue, but there are other variations that could exist in this set. So what I'm actually going to do is I'm going to partition E into 3 different categories. I'm going to partition it into white, blue, 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 white, blue, or blue, blue, white. And also it's important to note that these blues are distinguishable, so that has to be A and that has to be B. That's A and B, and A and B, so you can't have the same blue shirt person in these samples, right? So just keep that things in mind. So these 2 things, if we take the union of them, we should get the entire event space E, and it's impossible for those samples to intersect with each other, right? So it's impossible for a white shirt person to be selected first and a blue person to be selected first simultaneously, right? So this would be a partition of my event space. This is going to be this is going to make it extremely easy to count the size of the event space. So what I'm going to do is I'm actually going to begin by focusing on counting all of my white, blue, blue people, and then I'm going to focus on my BWBs and my BBWs, and then that comprises my entire event space. All right, so let's focus on our WBB set. So I'm just going to call this event 1, I'm going to call this event 2, and I'm going to call this event space 3. All right, so what is the probability of event space 1? So this is going to be the probability of obtaining a white and a blue and another blue. So from here we can use the product rule. So this is going to be equal to the probability of getting a white on our first draw, and then the probability of getting a blue, assuming that my first was a white, and then the probability of getting a second blue, assuming that I got a white on my first draw and a blue on my second draw. So how many white people do I have, or white shirt people do I have to select from my original sample? Well, there was only 4 out of a total of 10. So now that I have selected one person from my population, now there's going to be 9 people left to select from when I'm selecting my blue shirt person for my second draw. Now, since my first person was a white shirt person, that means that my next shirt person should be a blue, and there should be 6 remaining because I haven't selected any blues yet. Now that I've selected another person, the next is going to be equal to, so we're focusing on this, there's going to be 8 people to select from. What is the probability that it is a blue? Well, we've already selected one blue, therefore there's going to be one less of them. So once we multiply this out, that's going to be equal to 120 over 720, which will reduce down to 1 over 6. Right? So the probability of getting a white shirt person, and then a blue, and then another blue, is equal to 1 over 6. So that is the probability of event space 1. Now let us look at the probability of event space 2. So the probability of event space 2 is the probability of getting blue shirt person, then a white shirt person, and then another blue shirt person. So that's going to be equal to 6 out of 10, because there's 6 blue shirts out of a total of 10, times 4 divided by 9, because there's still 4 white shirt people, but one less person because I've already selected one, times, now I'm selecting another blue person, so that means there's 5 left out of a total of 8. Again, notice that it gives us the same exact product as the other one, because notice our bottoms are the same and our numerators are the same, just rearranged. And since this is multiplication, it shouldn't matter, right? So that should be equal to 1/6 again, right? So one could also use the same exact logic to realize that the probability of event space E will also be equal to 1/6. Again, you probably should have already realized that you could do this trick, or maybe just multiply one of them by 3, because the probability of A and B is the same as the probability of B and A, right? That is, these, or the intersection, is a commutative. It is a commutative set operator. That means it doesn't matter the order for which you intersection them, you will get the same exact set. So let us put all of these things together. So what is the probability of my event space? Well, we've partitioned it, right? So that means it's a bunch of mutually exclusive events. That means it's just going to be equal to the probability of E1 or E2 or E3. So since these are mutually exclusive events, we can just add up these probabilities. E2, E3. And we don't need to subtract anything because E1 and E2 are mutually exclusive, E2 and E3 are mutually exclusive, E1 and E3 are mutually exclusive, and E1, 2, and 3 are all mutually exclusive with respect to each other, right? So that's going to be equal to 1/6 plus 1/6 plus 1/6, which is going to be equal to 3 times 1/6, which is 1/2, or 50%. Now let us go back to our original problem. Well, actually that is our answer, right? Because that's the probability of E, which is what we were looking for, right? You could have divided by the original thing, because remember our original denominator was 720. That of course reduces down with respect to the size of our sample space, right? Where is that 120 located at? I'm not exactly sure, but I'm not going to go through that nonsensical, not necessary calculation. But this does come out to be our probability, which is pretty nice, but super extensive, right? So definitely a lot of calculations that went into this calculation. Is there another way? So think about it from this perspective. So we're gathering a sample of size 3 from a population of size 10. There are, let's see, what are we focusing on? Two blue shirts, right? So how many total blue shirts are there in our population? I believe there was 6, and we're interested in obtaining exactly 2 of them. Now, in terms of the interpretations of why I'm using K and X and little n and capital N, there's a distribution later that's actually going to enlighten you as why we use these things. But this is called the hypergeometric distribution of a particular random variable. So what is the probability that I get exactly 2 blue shirts in my sample of size 3? One can show that this is actually going to be equal to C, 6 choose 2, C, 10 minus 6, 3 minus 2, all over C, 10, 3. And what does this exactly correspond to? So the bottom is the combinations of 3 people chosen from 10. This is the combinations of all of my blue shirt people. This is the combinations of all of my white shirt people, right? So actually, once you work all this out, you're going to have 6 C choose 2, C 4 choose 1, and then C 10 choose 3, and you will realize that this also comes out to 1/2 in the end. So I leave to you as an exercise to sort of work through those combinatoric things, and you will get the right answer. So, if you do not know this special little trick, can you get the same answer? The answer is, of course you can, but there is the possibility of possibly missing something, which is why usually you would use partitions of your event and or sample spaces to make sure that the likelihood of you missing something is extremely low. But there are some special distributions and some special cute little tricks that you can use to make some of these problems extremely easier. But of course we can only present them in a case-to-case basis, but this is one of them. Now that we are a little bit more comfortable with the general sum and product rules for probabilities, now let us introduce a couple special rules that can use in some special circumstances. So remember that for the product rule, the probability of A and B can be found by doing the probability of A times the probability of B, assuming A has already occurred, or reverse the order for which the events occur, and do the probability of B times the probability of A, assuming B has already occurred. Instead of just looking at these as just different ways of finding probability of A and B, let's just look at these two things by themselves. So technically I could solve this equation for probability of A and B, or probability of B given A, dividing by both sides by probability of A, and that's going to give me the probability of B given A is equal to the probability of B times the probability of A given B all over probability of A. Or you could solve for the probability of A given B, and you're going to get a different representation. So that's going to be equal to the probability of A times the probability of B given A all over the probability of B. And either one or both of these formulas is what we refer to as Bayes' rule. And what they do is it reverses the conditional direction. So instead of you're giving one piece of information, you're now giving the other piece of information, and the individuals, of course. Keep in mind that these are equivalent to the representations using the intersection. So the probability of B given A is the same thing as the probability of B and A all over the probability of A. Or you could look at this other one as the probability of A given B is equal to the probability of A and B all over the probability of B. So these are also equivalent ways of finding the conditionals, but usually we do not know the probability of both happening simultaneously, which is where the aforementioned Bayes' rule usually comes into play. So now let's look at a particular example of where we may want to use this. So let's just write that out. So let us assume that we have 4 events. Let's assume V represents the event you have a virus, and let's assume V complement is the event you do not have a virus. Let's introduce a couple other things. Let's assume T is the event you test positive for the virus, regardless of whether you have it or not. And let's assume T complement is the event you test negative, or you do not test positive for the virus. So we have 4 different events. Let us look at a couple probabilities that these could be. Let us assume that the probability that you get a virus is equal to 23%. So of course the stronger your immune system is, usually the lower this probability will be. What is the probability that a test gives you a positive result? In the general case, let's assume that's equal to 37%. Of course, that's whether you have it or not, so it's really hard to interpret that particular thing by itself. What is the probability that you test positive, assuming that you have the virus? Now, this probability from a medical perspective needs to be as large and close to 1 as possible. Let's assume that's equal to 96%. So some people refer to this as the true positive rate for the test. Just some medical terminology that you may or may not be interested in knowing. So what is some of the questions that we could ask? So one could ask, what is the probability that you have the virus, assuming that you actually have tested positive for this virus, right? Because just because you test positive does not necessarily mean you have it. So if you were to do this 100 times, or you have 100 people, what percentage of the people actually have it, assuming that they have actually tested positive for it? So that's what the Bayes rule can actually help us answer, right? So using the Bayes rule, the probability of V given T is going to be equal to, so always, this condition pretty much acts as the sample space. So it's always going to go on bottom. And on the top, that's going to be the probability of V times the probability of T given V. So that's going to be the probability of V, which is 0.23. Probability TV, that's going to be 0.96. All over the probability of T, that's given to be 0.37. Multiply the tops and then divide by the bottom. You're going to have that's approximately equal to 0.5968. So that is one application that you could actually use for the Bayes rule, which sort of reverses the directions of the conditional probabilities for which you may or may not be interested in. The last special relationship that we're going to discuss for multiple sets of probabilities is what we refer to as the law of total probability, or LTP for short. So we begin by considering some arbitrary sample space S, and let us assume there exists some partition on that sample space. So remember, the easiest partition of a sample space is an event and its complement, because they span the entire sample space and they do not have any overlap. Now let's assume we have 3 or more, which is possible, where we have, for example, happy people, sad people, and people who are neither happy or sad, right? That would be a partition of, I guess, the mood of people. So you could have E1, E2, E3, and you could even have 4 or more. It doesn't really matter, but I just want to keep the picture fairly simple. So let's assume that E1, E2, and E3 partition the sample space S, and let's consider some other event A. Right? So this is going to be my event A. So is it possible that I can find the probability of A not by looking at A by itself, but actually the pieces of the puzzle associated to the partition of the sample space S, right? Because notice that I have, for example, this little region here. I also have this little region here. And I have this little region here, right? So I have 3 little pieces, all of which total up to my event space size, right? So how would I represent that in set notation? So the probability of A should be equal to the probability, so keep in mind the probability of A is with respect to the original sample space, right? But let's assume I don't have those pieces. So what I can do is I can do the probability of A intersection E1 plus the probability of A intersection E2 plus the probability of A intersection E3. Now it's possible that some of these sets do not have any overlap because, for example, I can have B over here, which doesn't have any overlap with E3, so that would be equal to 0. But I can represent the probability of B as the probability of B intersection E1 plus B intersection E2. That's perfectly fine. So, but this at least covers the entire partition, so this should total up to the original probability, which is where the word law of total probability comes from. Now, as I mentioned before, sometimes we do not know the simultaneous occurrence probabilities of A and E1, A and E2, A and E3, all of them or some of them, right? So we need all of them with respect to this, and that's not useful. But what we can do is we can use the product rule representation for each of these intersections, right? Because we can rewrite each of them as, there's two different ways, but the probability of E1 times the probability of A, assuming E1 has occurred. Now, why don't we use the probability of A times the probability of E1, assuming A has already occurred? Well, in that case, we would have to know the probability of A, which is actually what we're trying to find, right? So this is the only conditional representation for this product that makes sense. And then we have the probability of E2 times the probability of A, assuming E2 has already occurred, plus the probability of E3 times the probability of A, assuming E3 has already occurred, right? Because we do not necessarily know how often an event occurs in isolation, but sometimes we can usually find the probability of something occurring in the presence of others, or in the presence of other events in our sample space, right? So one could then have that long expression, but of course there's a more compact way of writing this. You can use summation notation, of course. For example, the probability of A can be represented as the sum of the products of the probability of EK times the probability of A given EK, right? Where EK, of course, are elements from the sample space, and EK form a partition of S, right? So this is what we refer to as the law of total probability. Okay, so with that being said, also let's just note this down because remember, sometimes it's hard to form partitions, but E and EC, the complement, always form a partition. Always form a partition of S. Okay. So with this being said, now let us look at just a particular example, sort of see how we would go about solving problems like this, right? So let's assume we have a sample space S, and let's look at our testing virus world, right? So we have a partition. Let's assume test positive, not test positive, so T complement, and then we have the virus V, and outside of the circle would be V complement, right? So V is this, right? So this is the V test positive and the V test negative, right? Ideally, that pink region should be super small, but this is just an idea of how to interpret it, because just because it's big doesn't mean it's wrong, right? Because maybe the testing needs a little bit of work, or maybe it has some error or something like that. So let's just throw some numbers in here. So what is the probability that you actually have the virus, assuming a few other things? Let's assume that the probability of testing positive is 37%. Let's assume that the probability that you have the virus, assuming you tested positive, is 71%. So that's our true test positive rate. And also let's assume that the probability that you have the virus, assuming that you tested negative, is really low. Of course, we want that to be as low as possible in practice. So from these pieces of information, what is the probability of V, right? So using the law of total probability, the probability of having the virus is going to be equal to the probability of testing positive times the probability of getting the virus, assuming that you have tested positive, plus the probability of not testing positive times the probability of having the virus, assuming that you have tested negative, right? Because why? Because T and T complement partition the space of S. But we don't have the probability of T complement, but we can easily find that, because the probability of T complement is going to be equal to 1 minus the probability of T. So it's going to be 1 minus 0.37, so that's going to be equal to 0.63. So that's the probability of not testing positive. So now that we have all of the pieces of our puzzle, then what do we have? So the probability of actually having the virus is going to be equal to 0.37 times the probability of V given T, so it's going to be 0.71 plus 0.63 times 0.04. And then once you work all that out, you should have the probability of actually having the virus. It's going to be approximately 0.9327, which is really, really high. right? So the likelihood of contracting this virus is really, really large. And that is the law of total probability. So we've discussed, pretty much all of the major rules that you could encounter in basic probability, in particular discrete probability. Um, but Bayes' rule also has another representation. This may or may not be useful. It really depends on what type of information you're given. So Bayes' rule alternative, right? So remember, the baby Bayes rule is the probability of E1, assuming E2, is equal to the probability of E1 times the probability of E2 given E1, all over the probability of E2, right? But now, using the law of total probability, we can express E2 as a linear combination of the probabilities of E1 and its complement using conditionals, right? So we can combine baby Bayes rule and the law of total probability into I guess you could call it a super Bayes rule if you wanted to, right? And what will that look like? So the probability of A given B, so I'm just going to use A and B instead of E1 and E2 just to make it a little bit more cleaner, usually is the probability of A times the probability of B given A all over the probability of A, but the probability of A can be found as the probability of B times the probability of A given B. Wait, that would be backwards, right? Because that wouldn't give us exactly what we want, so we would have to take the reverse direction. So that would be the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. So that would be the representation using the law of total probability for the probability of B. Okay, so this would be the grandparent representation of Bayes' rule, which sort of combines baby Bayes' rule and the law of total probability. And you can sort of think of some applications that you could use with this if you want. So those are the basic things associated to probability theory. You can make examples extremely difficult. Regardless, you could always solve this. Yes, those problems might be tedious, but these are technically the only rules that you'll ever need. Anyway, I hope you enjoyed this video. I will see you later when we actually start creating some special, cute little properties to make some problems extremely easy to solve. I'll see you then.